Hello, everyone. This week, we will be looking into CPU scheduling. So, readings for this lecture are from Dinosaur Book, Chapter 5 and Chapter 7 from Comet Book. So, before getting into the details of CPU scheduling, let's try to understand what is CPU scheduling. So, CPU scheduling is one of the main and fundamental mechanisms in multi-programmed operating systems. And why we need to do CPU scheduling? It's because to make efficient use of the most important resource in the system, that is CPU. So by doing CPU scheduling, operating system can effectively and efficiently make use of the CPU. So we actually saw an example of CPU scheduling in our lecture 3, where we saw non-preemptive scheduling. By this, I mean uh, the process, we never take the CPU away from the process. Rather, the process gives up the CPU when is not needed by it. Okay. So as we saw, this is the state diagram of the process. So the scheduler or the scheduling decisions happen either when the process yields the CPU, or when the process terminates, or when the process is blocked for some resource. Okay? So this is non-preemptive scheduling. That means we are not taking the CPU away from the process forcefully. So in other words, the process gives up the CPU. And however, we know that from our first lecture, most of the operating systems that we use now are time sharing systems, so which support interactive use, in which the user of the operating system gets a feeling that the user has the control of the entire machine. So the way time sharing operating system works is by optimizing the response time. So the response time of each process is minimized, is so low that we get a feeling that all the processes are running at the same time. Okay? And time sharing systems work by based on time slicing. Okay, so each process will be given a small time slice, and when the time expires, the processes will be swapped out and swapped in. Okay. So, however, in order to perform time sharing, can we do that without any hardware support? Let's think about this for some time, because we saw our first example in lecture 3, which is non-preemptive scheduling, where we do not need any hardware support, where the running process voluntarily gives up the CPU. Whereas in case of preemptive scheduling, we want to know when to take the CPU away from the process. Can we do that without any hardware support? How can operating system know when the time expired, right? So this is where timer interrupts kick in. So timer interrupts is the main fundamental mechanism of CPU management in time sharing systems. So a timer interrupt is generated by the hardware, hardware timer, and setting the timer require privileges, so that it ensures that only operating system can set the timer, and user processes cannot mess with the timer. And the timer interrupt, as the case with all the interrupts, will be delivered to the operating system. So timer interrupts kind of provide a way for the operating system to know when the time expired, or to know when certain period of time passed. Okay, this is the fundamental mechanism of time sharing systems. So time sharing systems use the timer interrupts for scheduling. The basic idea being, so before the process is moved into a running state, or when the process is run, OS sets the timer. Okay. So and when the process blocks or yields, or when the timer expires, operating system will know that the process needs to be scheduled. So it will pause the current process and brings back the another process. Okay, this is the basic idea. So the process state diagram in case of time sharing systems is as shown on the slide. So here, as we know, the scheduler additional scheduling decision happens not only when the process yields, Also, when the timer interrupt happens. So when the timer interrupt triggers, the running process is put to sleep, and then the another process will be scheduled onto the CPU. And how to do this, as we saw in our previous lecture, lecture 3, the process of switching CPU from one process to another process is called context switch. Okay, basically this involves saving the state of the old process, that is the running process, and then loading the state of the new process, the the process that we want to run. Okay, and we also need to know what state to store and where to store them. We also saw that for each process, operating system maintains a structure called process control block, where the state of the process will be saved. So we can save the state of the process into process control block. And we also saw that context switch. So this is the timeline of context switch. As we know, we save the state into PCB and we restore the state from another PCB and we continue execution. However, context switch is not free. There is a context switch overhead. That means there is work that operating system has to do to perform this context switch. And this work is not the real work. The real work is when we give the CPU to the process. So all the other work operating system is doing is kind of overhead because it is managing the process. The useful work is the work that is done by the process. So context switch has overhead. So because of this overhead, there are some considerations that we need to think of in case of time sharing systems or preemptive scheduling systems. For instance, timer granularity. What happens if we make the timer more fine grained? In the sense, what happens if we decrease the timer to, let's say, 1 millisecond? So that means every millisecond, the operating system has to incur the context switch overhead, right? Whereas if you increase the timer, like granularity of the timer from 1 millisecond to 10 milliseconds, then the overhead is decreased because now overhead happens only once in 10 milliseconds. Okay, so we need to, so operating system needs to make a decision to make whether fine grained granularity or to make the timer more coarse grained. And also operating system should know how to account for the CPU. So it needs to know how much of the CPU is used by the processes and how much of the CPU is used by the operating system itself to do the overhead, to do the context switch management. So in case of preemptive scheduling, we have, there is a mechanism that we know, that's the context switch, and there is a policy that we need to decide on. So mechanism is fairly simple, right? So how to do context switch? We all know. We save the state to a PCB and we restore state from another PCB. So policy is when to do the switching. So this is where things get really interesting. And as we saw in the first lecture, it's really good to separate mechanism from policy. So we should not tie these things together, rather we should keep them separate. And this actually leads to better design of the systems in general. And this principle is actually used in many components of the operating system, as we see later in the course. And is there a perfect policy? No, there is no perfect policy. We'll look at various policies and see how what are the drawbacks of different policies, because there are conflicting goals that we want to achieve. For instance, we want to achieve fairness and efficiency, whereas that's not always possible. We cannot get both at the same time. Similarly, we also need to be secure, and at the same time we also need to be robust. That's also not always possible. So there are many conflicting goals that operating system needs to handle when making when creating a policy. So few challenges of the policy is, for instance, the policy should be flexible in terms of job types. By that I mean the policy should be able to handle long and short running jobs, and also you should be able to handle interactive and non-interactive jobs, and also input output bound or compute bound jobs or even network bound jobs, right? So you should be able to handle different types of jobs in in streamlined way. And the issues in handling flexibility is we should also like make sure that the short jobs should not suffer because of long running jobs, right? So we need to be flexible. The reason is if we are not flexible, then short jobs might be waiting long time for the long running jobs, and users could be annoyed because if the job is not interactive, users could be annoyed. User might think that the program is stuck, although the program is not stuck, it's just never scheduled. Okay, so the policy needs to be really flexible. And the policy also should be fair. By that, we want to make sure that all users or all programs will get some CPU. Okay, so it should not be the case that like one process is starved of CPU, one process never getting the CPU, or basically it is taking long time for some process to get access to the CPU. It should not happen, right? And there are again some issues with the fairness. For instance, long-term fairness may not be same as short-term fairness. So the decisions that we take may seem fair in a short term. However, if you if you consider long-term effects, the decisions may not be fair. So the achieving fairness is not so easy. And specifically, any CPU scheduling policy has four goals that it wants to achieve. Ideally, it wants to it wants to make sure that it has all these four properties, at least these four properties. The first property is to minimize turnaround time. That means when a job is ready or when a program is about to be run, okay, and the time when the program finishes, that is the turnaround time, it should be minimal. That means the process should not be stuck. Okay, so when the process starts and the process completes, that's the turnaround time, and that should be minimal for all the processes that are in the system. Okay, that's the minimum, that's the turnaround time, and it should be minimum on average. When we take average across all the processes, it should be minimum. The second goal is to maximize throughput. That means we need to make use of CPU effectively. In other words, we should not be wasting CPU resources to do useless work. Okay. So throughput can be measured by like number of useful operations per second, where the useful operations are the operations needed by the processes, not the operations done by the operating system to maintain the processes. No. So we need to have maximum throughput. In other words, we should also have like maximum number of jobs completed per second should also be high. Okay, that's also maximum throughput. And other goal is to have short response time. That means when we submit the job, or like when the program is about to run, and when the program is first run, or when it gets access to the CPU first, that time should be minimal. That means the program should be very responsive. I mean, imagine if you try to open Chrome and Chrome takes like 2 minutes to start up. So you'll be annoyed, right? So we want Chrome or our process to start immediately. So the response time should be minimal. And finally, we want this CPU scheduling policy to be fair. That means we want to make sure that all the processes that are in the system should get fair share of the CPU. Okay, and also we don't want any starvation, and of course no deadlocks. So these are the four fundamental goals of any CPU scheduling policy. However, these goals often conflict with each other. Okay. For instance, let's look at response time versus throughput. So in order to have a short response time, we need to make sure that we schedule processes quickly, because that's when we can give this effect of being a responsive system, right? We should have shorter timer time slices. Okay, so that means we should have fine grain, finer timers. That gives rise to short response time. However, if we have fine grained timer, that actually decreases throughput, because now operating system has to do the CPU context switch every like more times. So that decreases the throughput. So these are conflicting goals. So minimizing response time is actually conflicts with maximizing throughput. Okay. Similarly, uh, fairness and turnaround time are also conflicting. So that means, in order to be, if you want to be fair, we may actually suffer from the turnaround time, and also the other, no, vice versa. That means if we minimize the turnaround time, we may actually decrease fairness. Okay, and for to understand various scheduling policies, let's uh, let's do very simplistic assumption that there is only one process or one program per user. Okay, and programs are independent. That means they are not exactly waiting on each other. There are no logs. Okay, so to understand the policies, let's assume that every user has only one process, and each process is independent. There is no dependency between multiple processes. Okay, so in the next part, we'll be looking at various scheduling policies. The things that we want to concentrate are, is there an optimal scheduling policy? So we will look at various scheduling policies, and we see which of the scheduling policies is optimal. Okay. Even like we don't need to optimize for all the goals. Let's even like given one goal that we want to optimize, is there any scheduling policy that will optimize for that goal? One thing that you need to keep in mind is whenever we are assessing uh, the effectiveness of a scheduling policy, we always should keep in mind that we don't know about future. That means we don't know what future process requests might come in. So we don't know what user might want to run in future time. So so the scheduling decisions or the policy that we want to understand, or we want to assess its effectiveness, we should also keep in mind that we don't know about the future. Okay? In the next part, we will be looking at various scheduling policies and try to understand pros and cons of each scheduling policy.